Okay students, let us try to solve this question. It says the electron energy in hydrogen atom is given by E is equal to minus 2.18 into 10 to the power of minus 18 divided by n square. It is n square joules. Calculate the energy required to remove the electron completely from orbit number 2. And then they are asking you what is the longest wavelength of light which is used to cause this transition, that too in centimeters. Okay, so there are two parts which we need to calculate in this question. Fine, so let us try to solve this. The solution for this goes like, you are aware the energy of the nth orbit is given to us as minus 2.18 into 10 to the power of minus 18 divided by n square joules, where n is the number of the orbit. Now here it is said that you need to remove the electron completely from orbit number 2. So your initial orbit is your second orbit and your final orbit would be, as they say, it should be removed completely. So completely word is used, so the final energy level you can take it as infinity because it has to be removed completely. Fine. Now you need to calculate the energy. So let us find out the difference of the energies. Whatever is the energy at the final state minus whatever ion energy is there at the initial state. So EF can be, that is energy at the final state, can be written using this formula which I have just now brought to your notice. So if we write this EF using this formula, it would be minus 2.18 into 10 to the power of minus 18 divided by n will be your infinity. So here it will be infinity square. Similarly, EI would be minus 2.18 into 10 to the power of minus 18 divided by your initial stage is orbit is 2. So it would be 2 square. These energies are in joules. So we can put these values here and we see that minus 2.18 into 10 to the power of minus 18 we can take out common and we can use this formula 1 by n final square minus 1 divided by n initial square. These are the levels NF and NI, orbits. Now minus 2.18 into 10 to the power of minus 18, 1 divided by infinity square minus 1 divided by 2 square. So this will now give us the value of minus 2.18 into 10 to the power of minus 18, 1 divided by infinity square is infinity, and 1 divided by infinity is equal to 0. Okay, so we take here 0 minus 1 by 4. So 1 by 4, 2.18 into 10 to the power of minus 18, this would be minus 1 by 4, or you can take it as 0.25. Okay, 0.25 minus. Now you are having this value, you multiply 2.18 with minus 2.58. Minus would be becoming your plus, and when you multiply this 2 you will get 0.5450 into 10 to the power of minus 18 joules. You shift the decimal point between 5 and 4, so you will get 5.45 into, as you are shifting the decimal point towards right, it would be 10 to the power of minus 1, which we add to 10 to the power of 18. So it comes out to be 10 to the power of minus 19 joules as the energy which we just now found out to remove an electron from the second orbit. Okay, now they are also asking you to calculate the longest wavelength of light in centimeter that is used to cause this transition. Now let us try to find out the wavelength which is helping you in this particular transition. So formula, now we know that delta E is equal to hc by lambda. So here lambda we can write it as hc by delta E. We will use this particular formula to find out the wavelength for this above transition. Now here your H is Planck's constant, value is 6.626 into 10 to the power of minus 34 joule sec, and your C is speed of light, which can be written as 3 into 10 to the power of 8 meter per second, and delta E we have just now found out above 5.45 into 10 to the power of minus 19 joules. So let us try to put all these values here in this formula. So you finally have lambda is equal to 6.626 into 10 to the power of minus 34 joule sec into 3 into 10 to the power of 8 meter per second divided by 5.45 into 10 to the power of minus 19 joules. Here if we talk of the units, your joules will get cancelled off, and your joules was here, it will get cancelled off, second will get cancelled off, so you will be left over with meters. So your lambda, that is wavelength, would finally after solving this would be coming in meters. Now when you multiply 6.626 into 3, you will get back 3. When you multiply, you will get back 19.878 into 10 to the power of minus 34. We add the power, so here it is plus 8 divided by 5.45 into 10 to the power of minus 19. Further, you divide 19.878 by 5.45, you get 3.647 into 10 to the power of minus 26 divided by, you are still having 10 to the power of minus 19 in the denominator. So this will end up as 3.647 into 10 to the power of minus 26. 10 to the power of minus 19 will come into the numerator as 10 to the power of plus 19. So we will add that, and answer finally you will get 3.647 into 10 to the power of minus 7. I told you would be in meters, but then if you will look at the question, they are asking you that in centimeters. So now we are knowing the relation between meter and centimeter. We are aware that 1 meter is equal to 100 centimeters. So here we will convert this meter into centimeter. So we will just write here 10 to the power of minus 7, which you are already having. We will multiply that with, this can be written as 10 to the power of 2 centimeters. So we will just write 10 to the power of 2 centimeters, because 1 meter is 10 to the power of 2 centimeters. Fine. Now we know how to calculate this. 3.647 into 10 to the power of minus 7 plus 2. So you will end up in the answer as 3.647 into 10 to the power of minus 5 centimeters is the wavelength required of the light for this transition from 2 to infinity, or to remove an electron from 2 to infinity. See, first we have calculated delta E, and then with the help of that energy which you got, you are trying to find out the value of your wavelength, which initially came in meters. See here, it initially came in meters, and then we have converted that into your centimeters as required in the question here. Here you need to remember 1 by infinity is your 0, and put the value and calculate. I hope you have understood the numerical. Thank you.